Well, hello everyone, and welcome to this Flex Talks in the series on medical manufacturing and supply chain. Today, Zohair Mekri is going to talk about using advanced simulation to optimize manufacturing and specifically discrete event simulation. He's going to talk for about 20 minutes, and then we're happy to take your questions. So please just use the Q&A button at the bottom. So take it away, Zohair.
Thank you very much, Patty. I appreciate it. Thanks for the introduction and welcome everyone. And thank you very much for joining. And thanks so much for giving some time to learn about advanced simulation. As Patty said, my name is Zohair Mekri and I'm part of the simulation team here in Flex. We'll be talking about a few things in today's webinar. We'll talk about what exactly is advanced simulation. We'll talk about why it's important to have discrete event simulation as a part of your process, why it's a good thing to have. We'll talk about how it optimizes, so we'll go a little bit into a very high-level technical overview of how the process works, and we'll talk about one of our success stories in our team that was garnering a lot of attention across the company, and internally and externally as well. And we'll talk about some considerations to keep in mind when you're looking at embarking on a simulation project, or when you're thinking about whether simulation is a good solution to have for your specific project or your case. So first, getting into what exactly is discrete event simulation. What you can see here on the right-hand side is what a discrete event simulation output looks like. But what essentially it's showing you is it's modeling a real-world process. So if you have a real manufacturing environment, if a real-world environment, and you have objects, you have those objects in a space, and those objects in that space are changing over time, the advanced simulation software, DES software, essentially is able to model those realistically using mathematical formulas and algorithms. What it's doing is it's taking the actual objects in the real world and it's relating them in the virtual world in different types of mathematical relationships. It allows the user to look at what's happening. So essentially, if you were to stand in a line and hold a software on your computer right next to it, looking back and forth between the physical line and the software should be exactly identical. And that's really what our team focuses on when it comes to doing some DES modeling, which is to make sure that the real world process and the process that's in the software, the virtual process, is exactly the same operationally and of course visually as well. So when we look at DES overall, there's a lot of considerations that make DES very beneficial. The first thing is that, as we said, that when you have your physical process and your digital process, it's essentially enabling you to perform a lot of different analysis on the digital process because you've been able to model it exactly the way it is in the real world. And what that does is it gives you the ability to answer a lot of what-if scenarios. So let's say that you have a process in the real world and you have a digital process, thinking about what happens if I need to add stations, what happens if I need to increase my volume, what happens if I need to balance the line because of maybe a design change. It really enables you to be able to take those what-if scenarios, those questions in your mind, and try them out first in the digital setting. And then once you figure out what happens and figure out how to do it properly and efficiently and in the best manner possible, go and translate that physically on the floor. And allowing for that to happen, because as we know, manufacturing environments are very complex. In the real environment, if you have to optimize or you are adjusting a line for some kind of a use case, it can become pretty complex very fast. So you can think of 100 or 200 ways to change that line, but you only have time to maybe try out 10 of those, but then you maybe only have resources to try out a couple of those, a handful, maybe 1 or 2 or 3. Simulation enables you to be able to do all of those scenarios in the software environment, in a digital setting. And so when we say for allowing for complexity, it truly allows for theoretically infinite amount of complexity, although it is bound by software and hardware requirements. But regardless, in theory, the permutations and the computations that you can perform are theoretically infinite, right? In any given scenario, in any given DES simulation that we do, we can run through hundreds of thousands of scenarios over a matter of just hours because the software is able to go through all those permutations and see which is the best scenario for that specific what-if question that you're asking. Now, naturally, since you're doing this in a digital environment, you don't have to do anything on the physical floor until you've decided what you want to do using your digital environment to figure out what's the best course of action. So by taking the thousands of different scenarios and having the software guide you in what are the best ways to do it, you can make all those changes digitally and then take those changes and then go to the physical floor. And so no physical changes are required on your physical environment until you are ready to do so. And so DES really fosters the ability for you to do that and creates it so that it's easier for you to understand what should be done necessarily to achieve a certain output or achieve a certain goal that was previously identified. Now, how exactly optimize it? So talking a little bit about how the process really works, how it goes through an optimization exercise, really. The way that it happens is that let's say that you have your physical line, and you can see here we have an example of one of a common SMT line, right, for our processes. And let's say this is a line that we want to optimize. Well, what happens is that the first step of the process is for us to gather data. So this step of gathering data is, of course, something that can be done by any teams and by anyone that is familiar with the process, or it can be done by the simulation organization. And what happens is the simulation team comes in, or the site, or the customer, whoever, and we gather the data. So we understand what's happening in that process, visually speaking, in the space, over time, what's happening to the process. Where are the machines? Where are the people? Where are the cycle times? What are the different operational metrics that are required that can characterize this line properly? And once that data is gathered, it goes through a very stringent data scrub. And essentially what we're doing in this is we're doing the traditional verification and validation process. Where we're looking at the data, we're making sure that the data is validated, it is verified, it's true, it's accurate, it's complete. Because in an operation environment, of course, there's a lot of things happening at once. We want to make sure that the correct data is captured. And that way, if we have the correct data in the sense that it is scrubbed, it's validated and verified, when the process is modeled digitally, it will accurately and correctly reflect what's happening on the physical floor. And that's very important because you need to make sure that when you're optimizing something in the digital environment, it's truly representing what's happening in the physical environment. So once that's complete, a model is created. Now, a model is created at this stage, visually speaking. We have not done any calculations or computations. We've not done any analysis. We've only modeled the process based on what is physically on the floor. The value for this is that now we have our base. Now we understand what's happening in the physical world, and it is modeled exactly the same way in the digital world. Once we have that, we go back to our line. We go back to the physical line. We talk to the subject matter experts, the customers. We make sure that we completely understand what is important in the process. As an example, we have to understand what are the variables in this process? What are the things in this process that the software, the DES software, will have the freedom to calculate and change based on things like the constraints of the line? So what are the things in this process that we cannot change? Those are constraints. Now they're bound by, it could be the user, it could be the customer, it could be the process itself, technical reasons, whatever that might be. But there are, in any process, there are a number of different things that can be changed and things that cannot be changed. So once those variables and constraints are identified, once they're properly identified, what happens is that our team takes these processes, takes these variables and these constraints, and we go back to the software and we start to essentially plug them in, and we create that model essentially that the DES software can then take and create a mathematical model. Now, this, of course, is an example model, and it's just talking a little bit about what's happening with the variables and constraints. But what's important here is that the software now is able to understand the relationships, mathematically speaking, between the variables and the constraints in a given process, in a given space, over a given time. And that's very important for the simulation software, because what will happen is that it will take this formula. Of course, like I said, this is a very simple one, but in the real world setting, the processes are much more complex. So the way that the simulation actually creates these formulas is magnitudes higher. But once it kind of understands what's happening in that setting, now it can start to understand what needs to be changed. And the engineer really has to come in here and start to apply a lot of their knowledge and their experience to how to tweak the software to be able to take this mathematical relationships between the variables and the constraints in a given process and start to either optimize or increase or whatever it is of the goal of the process or goal of the simulation to achieve it. Now, once that happens, the simulation software will take the mathematical relationships, the algorithms that have been created. There's a lot of programming that the engineer has to put in, because essentially what they're doing is they're creating an entire world. If you think about it, they're creating another digital world. And so there's a lot of computer engineering and application development that occurs, but the simulation software now understands that this is a process. The process has variables and constraints, and it has it in a given environment, and there are multiple factors at play that are affecting this process. And those different factors are what the simulation software starts to take into account. Once that's completed, the engineer goes into it and then starts to create the different types of combinations and permutations of that process. The DES software will then output various different types of scenarios. It will output various different possible solutions that can satisfy the variables and the constraints with a given goal and return that back to the engineer. This is where the team will come in and start to evaluate the different types of scenarios and then be able to understand which is the best course of action moving forward. Essentially, the DES software is giving multiple different options, but at the end of the day, the decision makers are the ones that are choosing which option is the best for the process, given business reasons, given current climate, given demand, or any other type of criteria that might be used by the decision makers. So if you look at this process in action, what happens is that we have a success story of one of our customers that had a few different problem statements that they were trying to address. The first one was that they wanted to increase their production volume. They were manually calculating this process, and they were finding that they were going to be achieving 5.5 million units per quarter. That was not the goal. As a matter of fact, their goal for this was to have 8 million units per quarter. But manual calculations were showing otherwise due to their process. What the other two main problem statements that they were experiencing was that they were having a key process station that had a very low utilization. They wanted to make sure that this utilization of this process was at a considerable amount because of the process that was performed at that station. They were also having some issues with equipment availability, so they had some equipment that they were using in the process that they wanted to make sure that they had available when it was needed. And so what happened is that the simulation technology was applied. We took DES as our solution, and we created a digital twin of the process. Essentially, what we did was as we explained in the earlier slides, went to the process. We understood the variables, the constraints, the objects in the space over time, and we modeled the entire process digitally. And we essentially created what we call a digital twin of the process. We were able to then take that digital twin and go through a number of different optimization scenarios. We ran hundreds of thousands of what-if scenarios on that process to figure out what was the best way to be able to achieve the goals and to satisfy the customer requirements in this specific project. As you can see, the goal was 8 million units per quarter, but the simulation was able to deliver 8.1 million units per quarter. It was able to increase the station utilization by 21%, and it increased the equipment availability by 15%. What this allowed to do was not only support the customer and their goals, but it was also able to support our team and our goals, which was being able to make sure that we were delivering the high quality product that the customer needed on time in the correct amounts. As a matter of fact, more than what they were looking for. So taking it all away, what are some of the things that you should keep in mind when you're trying to look at a simulation project? So some of the things to keep in mind when you're evaluating a simulation effort that will be occurring. The first thing, which is very important, is to understand whether or not simulation is even the solution. Now, discrete event simulation can be applied to any process where there's a step. Discrete event essentially just means being able to have a series of subsequent steps where things are happening in each step defined by a start and an end. So the first thing that you have to understand is whether or not your process is even the right process. In most manufacturing settings and most manufacturing environments, simulation can always be a solution. But there might be underlying issues, there might be underlying goals that might need to be achieved first. For example, the process might need to be defined, or the process might be changing, or it might be an automation problem, or it might be a material flow or quality or some other issue that might be occurring because of the design changes that are happening. Maybe the design of the product is continuously changing. So first, understanding whether or not simulation can be introduced at this stage is a very, very important thing to keep in mind. Of course, blanket statement would be that simulation can be brought in at any stage, but you need to make sure that it's brought in at a time where it can start creating value. It's very important to have the correct decision makers and the correct knowledge workers involved throughout the process, early on in the process. If you don't have people that are familiar with the process or the product or the goals or the problem statement, doing a simulation will not be able to deliver what is necessary or what is even desired by the decision makers of the process. So making sure that you have the right people at the right time, the right place is very important, especially when the simulation starts to form. When the discrete event environment is starting to be designed, it's very important that the people that are the decision makers are involved and are being able to guide the process of building that model. Very important thing is to understand what the problem really is. So defining your problem, sticking to it, and driving it is crucial to the success of any simulation project, and arguably any project. But sometimes when a simulation is introduced as a solution to a problem, sometimes the problem isn't correctly defined, or the problem is defined and scope creep occurs, where we have a problem statement that we started out with, but then the scope starts to change, or it starts to get added, or it starts to morph into something different. And it's very important to have a clear and concise problem statement when we start, and make sure that that is the goal that the decision makers, referencing point 2, have identified as the problem that they want to solve. Now, when we say problem, the scope, of course, could be increased. It could be a good problem to have, that you are having your volume of your product increasing. And so we need to be able to have the situation in which we can do that properly. So the problem statement is not always in a negative situation to be in. It can also be a very positive situation, but that problem statement is the scope, is the solution that the simulation is being brought in to solve. Sticking to it and driving to it is extremely important when you're trying to use simulation to achieve your goals. The process is the process varies depending on the product. Sometimes it can be different in different stages. And the scope can also influence the type of information that is required to make the simulation successful and to make the simulation valuable. So it's very important that the right information is collected for a project. Sometimes what happens is that the simulation is brought in, but it may not have the correct information. There's a lot of different ways to explain the phenomenon of having incorrect data come in and incorrect results being come out. And simulation is the same exact way. At the end of the day, discrete event simulation is a software, which means that it takes input and gives you output. So if the input is incorrect, incomplete, or inaccurate, then of course your results will be just the same. It's very important to understand that simulation requires not just a little bit of information, but sometimes a very large amount of information to give you a actionable or a productive insight. And so at the early stage, when we are looking at collecting the right information, that information may be larger in scale than usually assumed, because what will happen is a simulation will take into account multiple different variables, multiple different constraints, as well as the overall process. You have to make sure that when you're working with a partner in this area that you ask the right questions. Simulation is not something that you can do in your spare time or just pick up as you go. It is a very complex task. It is very multidisciplinary. It is extremely diverse in the terms of the skill sets and the ranges of those competencies required to be able to understand, build a model, to interpret the model, to implement the model. It's a very complex capability to have. So make sure that you're working with a partner that has the right amount of experience in the area, and you're asking the right questions in the sense of what you're trying to do. last but not least, it's always about people. It is always going to be about the power of your knowledge workers. It's always going to be about the people that you're working with, the people that have the experience and the information to be able to create, interpret, and implement the right solutions using technology, because they are the most important factor when it comes to doing any type of simulation project or any project in general. But simulation itself is a very, like I said, a complex task. And so being able to have the right people with you that understand this process is extremely important. So make sure that the team that is involved is crucial to the success of the overall project. That being said, what we'll do now is open up for some questions and answers, and of course say thanks for listening. But we're interested to hear if there's any thoughts on what we talked about.
Thank you, Zohair. That was really interesting. And I'll leave some time for questions, but I actually have some if you don't mind.
Sure.
So what kind of production parameters tend to get the most significant changes? You know, like if you're just starting out, you go, I'm really interested in this, but where do I start?
Absolutely. So, I mean, over the hundreds of projects that our team has done, right? I mean, there's been a lot of different metrics that can be affected and that can be positively affected by simulation. But there are trends that occur, obviously, right? You know, you can have projects where headcount is being optimized, right? And when we say headcount optimized, it doesn't mean that you are removing or adding. It can mean that you're moving them around. It means that you're adding more headcount. You're making the process more efficient, which ties directly into direct labor efficiency, right? What are the people doing? What are they actually working on the line? So being able to work with people, simulation really pulls into the power of humans, as we were just talking about, right? Equipment efficiency is a big one. Sometimes you have a process where you have to have equipment that's becoming either lower utilized or it's being utilized too much. So you need to make sure that you adjust and balance the line properly. As you saw, our success story was one of those examples. You know, sometimes when you have a big facility, you know, you have people that are walking across, right? They're moving material. Material flow is a big thing. So material flow simulation is a very affected area when simulation comes in. The travel time, the distances that are related to that, those are some common metrics that happen. Space, because like we said, like a big factory, you know, needs to be set up properly. So simulation will guide you on how to do that. So a lot of our projects do have space utilization criteria, and of course, you know, that directly relates to the efficiency of the overall process. So there's a lot, but those are some of the key ones that we see in our experience.
Okay, and then are there production scenarios actually where modeling is just not suitable at all? So don't even try.
Well, production inherently is a discrete event, right? So production flows, production processes, they are by nature, they are discrete steps, right? There's one station, two stations, three stations, and they're all doing a discrete action, which means that there is a start of the action and an end of the action. And so discrete event simulation is aimed at discrete events. And since production is inherently a discrete event, simulation is a very strong option there. As a matter of fact, a lot of simulation technologies that were formed in the industry were formed around manufacturing. And so in terms of simulation, there really isn't a process that simulation cannot handle. Anything that has steps is pretty easy. What we will say is that simulation is where simulation starts to become something that may be a little bit more difficult is when there's a lack of information. So if you don't have information about your discrete event, then of course modeling that will be a little bit harder. But inherently speaking, production is the best suited scenario for things like simulation technology.
So then that sort of begs the question about, you talked about DES. Are there other types of simulation?
There are, as a matter of fact, in Flex, we have 3 different types of simulation. Discrete event simulation is the one that is our most, I would say, is our strongest and core competency. Of course, we have other types of simulations such as finite element analysis, which is more of a design simulation, physics-based simulation. We have very, very strong industry experts in this area. As a matter of fact, we have a large number of FEA experts and engineers throughout Flex who are known in the industry for being absolutely fantastic in terms of FEA. And the last one is design for reliability. And we have a very large and comprehensive DFX capability where design for reliability falls into. And that simulation is looking at the reliability of components in a product, I should say. And that is also a very strong capability in Flex. But overall, those are the three main simulations that Flex has. Simulation in general can be broken down into multiple different areas, but they usually fall under product simulation and then process simulation.
Okay, well, I don't see any other questions, but I did want to mention that the example that you gave, it was a Class 2 diabetes product, and it actually won an award from
Yes.
the Manufacturing Leadership Award. So congratulations on that. Good work.
Thank you. Thank you very much.
Well, thank you so much. And thanks everyone for your time. And as you can see here, if you want more information, there's Zohair's email, or you can also email healthsolutions@flex.com. And we hope to see you next month in the second week of June, when we're going to talk about front-end collaboration in medical product design. Thanks so much for your time. And thanks again, Zohair.
Thank you, Patty, and thank you everyone for your time.